Hello, everyone, and thank you for joining us today. My name is Jeffrey, and I'll be your host for today's webinar on achieving flexible, high-performance data lakes with Xilinx, Samsung SmartSSD, and Bigstream Hyperacceleration technology. Today's presentation is scheduled to last roughly 45 minutes with 15 minutes or so at the end for Q&A. Please type any questions you may have in the Q&A section, and we'll do our best to answer you at the end of the webinar. And before we begin, here are just a couple of tips and tricks about the interface. To enlarge any individual window, click or tap on the square in the top right of the box. If you're having trouble with your audio, you may need to adjust either your device's volume or the volume in the media player you can find at the top left of your console. You'll also see on your console our resource list for today with a PDF copy of today's slides, as well as a link out to a blog that we have recently put out, and more resources on Xilinx data center solutions, as well as our previously run webinar page that you can now view on demand. So this webinar will also be made available for on-demand viewing later today, and you can find that via the link that brought you here or on xilinx.com/webinars. Really quickly, before I throw it off to Dan, I'd like to mention our survey that we have on the left-hand side, and that will really help us out to bring you the best content that we can. And with all that housekeeping out of the way, I would like to throw it over to Dan to begin our presentation. Take it away.
Thanks, Jeffrey. My name is Dan Eaton. I work in business development at Xilinx in the database and data analytics space. And what we have today is Xilinx is the worldwide leader in FPGA accelerated computing with use cases ranging from networking and security, database and data analytics, which we'll talk about today, video and image processing, AI inference, and in life sciences. We've got a growing ecosystem of accelerated computing solution partners. And if you're interested in joining our ecosystem, please sign up at the Xilinx Accelerator program on the Xilinx website. And today we've got FPGA accelerated platforms from Xilinx available in Amazon, Alibaba, Microsoft Azure, in Nimbix, as well as from a large number of server OEM vendors. And today we're going to talk specifically about Samsung's exciting new product, the SmartSSD. All of this is made possible by Xilinx unified development environment, Vitis. And with Vitis, developers can leverage Xilinx hardware platforms in the cloud and on-premise, leveraging our drivers and runtime, our compilers, analyzers, and debuggers, as well as accelerated libraries, Vitis libraries that are available across a number of domains, including compression, security, database, computer vision, as well as math and industry-specific libraries such as fintech. With that, I'm excited to introduce Roop Ganguly, Chief Solutions Architect of Bigstream, who will provide us some insight into how customers can use Bigstream running on Xilinx-powered Samsung SmartSSDs to accelerate data lakes. Take it away, Roop.
Thanks, Dan, for that introduction. Thank you, everyone, for coming this morning. Again, my name is Roop Ganguly, Chief Solution Architect at Bigstream Solutions. We're a software partner of Xilinx, and today I'm going to be talking about accelerating data lakes for performance using Samsung SmartSSD technology along with Bigstream software to make that happen. So what we want to get out of today's talk is, first of all, just a basic definition of data lakes. in case you don't know, and then talk about some of the performance issues that data lakes face when we're trying to implement them, and then how acceleration in general and Samsung SmartSSD can be a key solution in that space. Excuse me. So when we talk about a data lake, I've got a definition here. Basically just pulled this from the web. A data lake is a system or repository of data stored in its natural raw format. So what does that really mean? It's really, I think about it as a staging place for data for fast and ubiquitous access by a number of roles within the data analytics organization, right? So it's where data is organized, cataloged, provided, and so it's the hope is that it's at the touch of your fingers from the data scientist perspective. So full disclosure, I was a data scientist about 5 years ago in digital media, right? And I remember, when I was doing an analysis for my VP, who was presenting to some other external customer. I'd need to go desk to desk to figure out where data was, right? So I'd say, hey, Fernando, you know about this ad tech data from Yahoo. What format is it in? Where is it stored? And he'd come back to me and say, oh, it's in a Vertica database like this and this. Here's the name, and you got to log in. And then I'd go to Linda and say, okay, the credit card data, I need to do a join with a couple of fields from the credit card data. Where is that stored? That's how that's how I used to do it. And so it would have been nice to have, a central repository, cataloged online, clickable, where this data, is staged. And I think that's the basic idea of a data lake. So, when we think about it, it's, usually maintained by data engineering in sort of medium to large organizations. And from our experience, it's between 1 and 100 terabytes, at scale of data ingest per day. And again, it's sort of where all the data is stored. So, typically beyond cleaning, cleansing, null removal, it's, most of the data is there for whatever uses that the analytics folks want to use it for. And so it supports many data analytics AI users and specific roles, and we'll get into those. So, one of those roles that uses it is the data analyst. These are folks that are providing business intelligence, for example, either internally or even externally. I would provide my analytics to actual customers, but there's also internal customers that consume the answers these analytics produce. And, they typically have either batch, what we call batch, which are basically, large look-back analytic queries. How many people visited Taco Bell in the last 6 months, and what other fast food restaurants are they going to, with location-based data. That's something that I used to do. So these are large-scale queries that, sort of run overnight. They also can do ad hoc queries, which typically are quicker, maybe a little more complex against this data that might be at a data lake. I've defined a role called data scientist, and these are typically AI users that are looking at the strategic direction that the data can advise on. So basically, training models for example, we want to know the behavior of this particular ad tech data producer over time, with seasonal considerations, hour-to-hour considerations, economic condition. We want to marry that data with economic condition. So they would build models for these things. So that's another set of users for a data lake. But really, for all three roles, when you think about a data lake, performance is a key component vis-a-vis productivity, right? Usually these folks have either SLAs or, like I said, I had a VP waiting on the output of my analytics. And so performance was important, right? I had to get the answers by a certain time. And, typically what we've seen is that in order to get more performance, we scale our cluster, right? Or we do some kind of time sharing. So the data engineering can use the cluster overnight, and, it's blocked off from 2 in the morning till 7 in the morning. And then the data scientists can come in and start using it things like that are the approaches for performance. What we're going to talk about today is acceleration as an attractive alternative to sort of normal cluster scaling, attractive in a number of aspects, including power, including cost, and ease of use. And today we're going to talk about the Samsung SmartSSD drive, which is a computational storage device, and I'll get into what that means. But it's basically a device that has computation, storage device that has computation directly on it, in line with the data, and so that gives you a number of advantages. Okay, so let's look at a conceptual current data lake architecture. This is what they look like. Again, this is a very general picture. Yours may vary, but typically we have a bunch of data, as we said, potentially terabytes of data coming in daily on the left side there, right? And so this can be unstructured data, things like tweets, web pages, or they can be, business or custom apps from databases. So in my case, there was ad tech auction houses that would give us data in a particular format, say CSV, which was structured in that regard. But typically, these are huge storage and computation infrastructure is needed for this. This is often shared with the analytics piece, and we'll get into that. But today, what we're seeing, I would say in our exploration of sort of the customer space, market space, it's usually spinning disk for this volume of storage, HDDs, and then, like a number of CPUs, clusters doing the work that stays the data lake. And on the right side, we see the users, right? And we mentioned these roles already. So the data engineers are the folks kind of working in tandem with the DevOps, the infrastructure folks, to do the data preparation, right? They're cleansing the data, they're getting rid of bad rows, they're doing, a null elimination. They're sometimes it's even sort of eight arrangement of the data, preparing the data in a structure that's usable by the other two roles. And then we mentioned the data analyst, who's doing ad hoc batch queries and reporting for some business objective, either within the organization or external to the organization, if you're an analytics provider. And then the data scientist is training these AI models, right? Either deep learning or machine learning algorithms. And so what we're talking about today is the pain points, right? I mentioned my pain point was that I didn't know where the data was, and then I had to stay overnight to do my analytics. That's the middle guy. But for the data engineers, they have certain SLAs. These tables have to be prepared by this amount of time, have to have this amount of look back, and so performance can be an issue for them. And then the data scientists, typically in training the model, these are huge data sets and complex feature sets that they're working with, and that can be very sort of performance intensive. So those are the pain points that we talk about with the data lake. So let's see what we can do about that. So I mentioned the concept of hardware accelerators, and this slide is really for folks who aren't familiar with accelerators. And what are they really? They're really a specialized hardware, and they come in different flavors. So FPGAs, GPUs, and ASICs. People have probably heard those names. And what they're really designed for is efficient executing of what I'll say is specialized code. So unlike a general CPU, right, they're not meant to run an entire operating system and play your first-person shooter video games, right? They're able to be programmed at a hardware level, really at a gate level, at a logic level, to have the architecture you need to solve your particular problem. And so that makes them very efficient, right? So you talk about reduced instruction set computers, right? These are specified instruction set computers. The instruction set there is really specified to your application. So they're very, very efficient. So they provide performance. That's really how they provide performance. And in the case of FPGAs and GPUs, they're field programmable. ASIC is a different sort of flavor where that hardware is hard coded as soon as it comes out of the factory, right? They're very efficient and they have power characteristics that are favorable too, but they don't have the flexibility of field programmability. But the important thing there in that second bullet is, if the user is capable, and that's what we'll get into in terms of the acceleration solutions we're presenting. Like I said, they can have both power and cost advantages. It's cheaper than buying, I mentioned scale up or scale out. It's cheaper than buying a more expensive server or buying a number of more servers. And they're designed these days to physically attach to just existing servers. So they'll fit right into your PCIe slot. Your computer, your server sees them as a resource that they can run stuff on and get performance from. Again, that programmability is an issue, and we'll talk about that. If you want more information, we just posted and will be posting a blog post at Bigstream. There's a URL there with our latest blog post comparing FPGA and GPU acceleration. So I recommend you check that out. If you don't have to memorize that whole link, you can just go to blog.bigstream.co and check it out. Okay, great. So acceleration is the solution. Let's put them into our data lake, and we'll be good to go, right? So what we've done is we've added accelerators to our servers. They're accessible by the data lake providers, the people that access them. But for some reason, our three friends over here in the data analytics organization are not smiling, right? There's still a problem here. And so the pain point that remains when you do acceleration, especially from the data analytics perspective, right? We're talking about the data analytics user, is these accelerators are typically pretty complex to program. It's not your average, even C++. Like these folks, myself, we're using Scala, your Python, your Java to do our analytics. And I'm raising my hand right now, I had no idea how to program one of these accelerators. So you give me one of them, sounds great, but I don't know how to program it to accelerate my analytics. It's just not something that an analytics person would be trained for, right? You need sort of specialized hardware training to program it. So a pain point remains even after we added accelerators to the picture. So let's get into that a little bit. So the inhibitor that we're looking at is, the way to think about it, it's the programming model gap that's inherent in the technology for acceleration, right? As we mentioned, those data scientists, the folks in the upper right, your finance, your fintech, or me as an ad tech, the data analytics person, we want to use our big data platforms in the white box there in a very domain-specific way, right? I was an ad tech. It might be a healthcare analyst. It might be a financial analyst. We want to program in a high-level language, Python, Scala, Java. Analysts don't really want to, and I would argue a fair number, just based on experience, 90% don't know how to program the kind of hardware at the bottom for acceleration. It's just not a skill, that you develop. Now, a lot of these organizations might have in the lower right there performance engineering team. Now, those are the folks with the wherewithal to program this kind of hardware, but they have the opposite problem of this gap. They don't understand the domain very well. They're not financial experts. They're not ad tech experts. So you really end up, and on the right side, in terms of HR, with a skills gap, where these two groups, the data scientists and the performance engineers, have to work together to accelerate an analysis. And that can cause complexity and cost and, basically overall headaches. And the last comment I'll make here is that this is really happening, right? We're seeing this, especially in sort of the larger organizations. So this gap exists. So what Bigstream has developed to address this is the Bigstream Hyperacceleration method, okay? And at a high level, what you want to think about is that it automates this process of acceleration for the user. And so just a quick word about how it does that. So I'm sure folks are pretty familiar with those big data platforms in the white box, if you're attending here today. All of those big data platforms, at the end of the day, what they produce from that high-level code, right, the Java, the Scala, what they produce is a data flow. And I'll just define that for you. It's a data structure. It's a DAG, direct acyclic graph. And what it does is it contains all the information about the analysis that the user wrote. It has operations that they're using, concurrency information, result production and consumption information. All that stuff is encoded into this DAG. So forget about Bigstream for a second. These big data platforms produce that on their own, right? They do that in order to distribute the computation across, for example, a cluster of CPUs, right? So what Bigstream has done is, seizing upon that, we take this data flow and essentially compile it we analyze it and compile it, enrich it, and then program it automatically onto this kind of hardware for acceleration. Okay, and so we can talk about up to 10x acceleration, in some cases, and that's going to depend on the operations you're using, the data formats you're using, the hardware you're using. But that's the sort of upper range of what you can see. But I think equally important, in my opinion, is in the upper right there, is a zero code change, right? So we don't want to affect the data scientists or data analysts' work processes, right? We don't want them to have to use a compiler pragmas or a particular dialect of SQL, or even worse, do like data grooming or data preconditioning. So this all really happens under the hood. And so that's how we're trying to overcome this programming model gap that we see through acceleration. And just one more comment about this is really this is a framework here, right? So what we've done is we've made this 3-layer architecture, and it admits different big data platforms and different hardware platforms, as you can see. Right now, we're in the state of the art. What we accelerate is Spark SQL. We have some Hive support and Kafka connector support. Presto is actually roadmapped at this point, as is the GPU. We support all 3 other hardware platforms: CPU, SmartSSD, and FPGA. And today we'll be talking about the SmartSSD acceleration. Okay, so I mentioned the Samsung SmartSSD platform. This is a schematic for it at a high level. And as I mentioned, what's interesting about it is that it's a storage device, right, an SSD, that has a computational element in line with the storage. So you can see right there, there's an FPGA right on the storage platform itself. Okay, so why is that useful, right? Really, there's 3 things you can get out of it. One is that any computation that you're able to do on the storage, on that FPGA, is offloaded from your CPU, right? So you plug this into your CPU server, and now when you run your analytics, some computations are put onto the storage itself, and so the CPU is freed up. CPU cycles are freed up to do other useful work. The other thing is basically high performance. As I mentioned, these FPGAs are very high performance when programmed properly and can outperform CPU in terms of instructions. And then the third interesting thing is that since the data is being processed right on the storage, right? So if you do a filtration of that data, projection, column reduction of that data volume is reduced. And so the data that leaves the storage in the computational storage world is much smaller than the full data that would have had to be shipped if you didn't have this computation element on the storage, right? The other cool thing is that you can picture kind of a 3-way switch between the SSD and the FPGA, kind of an internal network there that can be configured. If you're not using acceleration, you can make this device just a normal SSD storage device. And so where Bigstream comes into the picture is that we are the partner that Samsung selected to do in the analytics, right? We're going after the analytics user in this case. And so in order to program that FPGA with the semantics from an analysis that a user wrote, Bigstream is the vehicle to do that. So we, again, exactly in the same way as I've shown, we bring down, using that DAG compilation approach, the program onto the FPGA on the storage and execute it. And I'll get more into sort of the details, but we'll do a little bit of a detailed dive into exactly how this works. But we're very excited about this platform in support of data lakes in particular in this case. Okay, so let's go back to our data lake picture and check out our three friends over here. So now what we've done is we've upgraded the data lake with Samsung SmartSSD. So we're actually getting performance in sort of two ways with this. One is the upgrade to a faster storage technology, right, the flash storage technology over the spinning disk. And then we also are getting from the Bigstream piece on the FPGA, we're getting computation offloaded from these CPUs onto the SmartSSD and executing very fast on a specialized piece of hardware, the FPGA. So now what we're getting is the filter, decompression, some SQL elements. If you look at the SmartSSD, eventually, and I would say sort of roadmap is, eventually we putting ML models and doing training on the computational storage. That's not something we've done yet, but there's no reason we can't. So right now we're starting with sort of filter, decompression, projection, format processing on the FPGA. But you can get, as you'll see, you can get a very good performance boost from that. And so now our friends are all smiling, right? So the data engineer, his ELT is running much faster because the FPGA is accelerating the data format processing, the filtering that he needs to do, the data cleansing he needs to do, and also the CPUs are freed up, and maybe we don't have to cordon off resources for that piece. And then on the consumption side, the analysts and the scientists are able to run their analytics faster, again, by offloading the computation onto the FPGA, which is in the storage. And then, the pain point has kind of gone away in this case because there's zero code change. These folks are programming exactly as they were before and exactly the language they were before, and all they see is acceleration that comes from under the hood because we're working at this data flow layer. We're compiling from that data flow, so we can't touch these user code even if we wanted to. And so that's the picture of the accelerated data lake using SmartSSD. So just to show that this actually works, we've got some performance results. These are benchmark performance for batch analytics. It's a benchmark suite called TPC-DS. It's available from tpc.org. You can go and check it out. They're basically business intelligence queries. There's a set of 104 of them that are used. They're pretty ubiquitous for testing systems under test for performance. And they cover basically all the SQL operators, all the flavors of join, all the filters that you can think of. So these are the top 40 queries. What we did is we ran, and I can give you the server config if you ask, but we ran on a server with a single smart SSD, again, attached as a PCIe component. And so we can run, with Bigstream running the computations on smart SSD, versus just running on the server with the CPU. And you can see on average we're getting a little under 5x speed up for these queries. Again, this is in Spark SQL. A couple key things to note is that this is 200 SF JSON data, which is probably around 200 gig. I have to check that. 200 gigs of data. So that's pretty sizable for a single server experiment. And this is JSON data, which is a row-based data format. So that's the batch analytics piece. So that's what's sort of pleasing the data analysts. Another interesting experiment we did was for what I call ad-hoc queries, and this is interesting because the data format that we're processing here is Parquet. Now, for those aren't familiar with Parquet, Parquet is a columnar format of data, so it's stored column by column, and it's actually known to be, there's a lot of movement towards storing data in Parquet because it's known to be efficient via compression and metadata and other reasons. So it's actually a pretty aggressive baseline to be comparing to. And in this case, we did some ad hoc queries in a very realistic data science kind of way, and we're able to get sort of greater than 3x speed up, which we feel is pretty impressive. So this particular experiment, again, we're comparing. On the left side, you see just running Spark on a normal SSD drive, and on the right side, we're running the exact same server, but with SmartSSD SSD drive doing the processing via Bigstream. Again, the interesting thing about this one is if you look at the top level on the right side, we're using Tableau, which is a typical visualization reporting tool that data scientists use. Again, the exact same query. So the Tableau user, the data scientist, does not see any change running on the left side or the right side, just sees the performance. And this particular analysis was using Caltrans highway sensor data from 2010 to 2019. We designed a couple of queries. Let's say we wanted to analyze 101 south traffic over that 10-year span, and then switch to I-880 north traffic. So we had a couple of queries that we designed sort of in a realistic analytics scenario. So again, I mentioned that we got sort of greater than 3x performance. So you see data scientists unaccelerated on top is running the queries, going to a standard SmartSSD in Spark, and then the accelerated data scientist is running using the SmartSSD drive. And we got between 3.5 and 3.7. I think query 1 was 3.5 and query 2 was 3.7. But then you also get the other benefits from this, right, which were the CPU offload I mentioned, PCIe savings, and again, we're using the exact same Tableau code. You can write SQL in Tableau, and it'll send it to Spark via a protocol. That's exactly what we're using. So these two were using exactly the same Tableau setup to execute this. So that's the cool aspect of it. So let's just get a little bit deeper into exactly what's happening here. Why are we getting this performance, right? And so what we did here was for query 1, we created a timeline. One is the standard SSD timeline, and the other is the smart SSD timeline. And so hopefully from this, we can understand exactly where the performance is coming from. So if you look at the standard SSD timeline, what happens, right? I issue my query from Tableau. It goes over to the server. Spark actually processes it, and then we have to transfer the full data from the storage onto the server, right? So the entire table is in memory, or if it doesn't fit, it's sort of partially memory, partially in disk. And then we have to, on the CPU, execute the filter and decompression and the SQL processing, and then we return the result to Tableau, and then it does its visualization thing, right? That's not included in this time. So that's the steps that happen with the standard SSD. And when we switch to the smart SSD, right, we issue the query, Bigstream catches that data flow and says, hey, the filter and decompression, I have a smart SSD FPGA available. The filter and decompression I can do right on the storage. So when we go in a matter of milliseconds, I will program that FPGA to execute that filter and decompression on the storage. And then what happens there, right? So we're filtering based on the highway that we're doing and other factors. So that data gets reduced right on the storage and in a shorter amount of time on that via that FPGA in Bigstream. And then the data transfer, another added benefit I mentioned, is much shorter, right? We've already filtered out all the other highways data on the storage, and now we're transferring only the 880 data and the, I believe, 101 data that we were interested in back to the server. Then the server can execute the SQL processing. That takes approximately the same amount of time in this case because we're focusing on the scan. In fact, when we start adding more and more SQL operators to the Bigstream palette, the Bigstream library for the FPGA, this can be shortened as well via this approach. And then, we return the exact same looking answer back to Tableau at the end of this. And you can see it took much less time. So 214 versus 61, that's approximately a 3.5 x speed up. So I hope this is illustrated how this technology applies to specifically to data lakes, but really sort of any computationally heavy analytics scenario you can think of. But today we were talking about data lakes with SmartSSD. And thank you all for listening, and we'll take any questions. Thank you.
Thanks, Roop, for that presentation. And if any attendees have any questions, you can submit those via the Q&A box. And we'll begin. We've got a few different questions from the audience. The first question for Bigstream is, are all the frameworks and libraries shown in slide 13 already accelerated inside of the SmartSSD, or only Spark SQL? What about MySQL?
If you don't mind, I'll go back to no. Like I mentioned, the Bigstream picture is really this one. So like I said, it's Spark SQL, some high functionality, and we do have the Kafka connector. And I mentioned the Presto is on the near-term roadmap. So that's the state of the art currently. But like I said, it's an extensible framework. So if we think about things like, you asked about MySQL, Dan, was that the question?
Yep.
Yep. That's not currently roadmap. But again, we grow this by customer need, right? So if a need comes about, we'd be able to do that.
Sounds great. Next question. Does Bigstream Solutions support SNIA computational storage service framework and API model?
I am not familiar with SNAI. If it's a different computational storage, I mean, the framework would support that in sort of the same way, but we don't support that particular platform at this point. The only computational storage we're currently working with the Samsung SmartSSD.
Okay, great. Next question. The SSD storage can be seen as a file system where we deploy, for example, a Docker with Apache Spark SQL accelerated. Or I guess the question is how to obtain the accelerated version.
How to obtain? So there's, in terms of working with this technology?
Yeah.
Yeah, so basically contact us. There's a couple different ways we can do that. So for an on-premise deployment or POC, that's obviously available where we would provide example hardware for the customer to use. But we're also looking at developing or putting our solution on Nimbix Cloud. We actually already have. There's been some reconfiguration. So if people aren't familiar with Nimbix Cloud, they basically have accelerated instances. So they have Xilinx Albio instances, and they also have SmartSSD instances where you could definitely try out this technology. In fact, I believe, don't quote me on this, but you get your first 100 hours of computation free there. So it might be, that's a good place to start with if you want to get working with this technology. And again, Bigstream, you mentioned Docker. We actually have a Docker image there that's just available. So the way they do it is they have Docker images available as what they call applications. So you start up your node, load that application, and you'll have Bigstream automatically there. So it's an interesting approach. We are looking into getting into Nimbix, so that could be a viable alternative. But to start off with, I would suggest contacting Bigstream.
Awesome. Next question. Of the queries that you showed in the TPC DS benchmark, were there any where you ended up slowing the workload? If so, do you have any explanations for why?
That's a helpful question. The answer is no, we didn't slow down any. But if you go, beyond the top 40 to the all 104, there were some that only got maybe 20% or 30% acceleration as opposed to the numbers you're seeing here. And the reason for that, to your why point, is we currently are focused, especially on the FPGA and SmartSSD solution. We're focused on file scan, data format, parsing, filtration, projection. I believe aggregate might be our next. But like I said, we're growing our operator space according to customer need. And so that's why you see this spectrum of different performance, because these queries utilize each of these queries utilize a different amount of those operators, right? So the answer is no, we do not slow down any, but hopefully I've explained why there's a spectrum of performance here.
Yeah, I think you did. That's very helpful. Next question, and this is more a question for Samsung, but Roop, you might know, does SmartSSD support RAID storage? If so, what types?
I believe it does, but I'm not an expert on RAID. I don't know, Dan, if you know anything about it. But you know, if you pose that question, we can get it to Samsung and figure it out. You should be able to stripe your data across multiple SmartSSDs. It's definitely the case that I mean, the answer is yes. We have striped data across, maybe not in a strict RAID configuration. But I need a little more technical support to answer your question fully.
Okay. Next question. Are the computational offloads fixed functions, i.e. fixed compression algorithms, or is it dynamically programmable?
Great question. So we can get into a little bit more of how the actual programming works. So the answer is what they are is operator templates, right? Actually, sequences of SQL operator templates. So they basically, let's say your SQL code does a scan of 2 data sets, creates 2 tables, does a join, and then a filter, right? What we have is a template, a piece of code, a piece of FPGA code that matches that sequence of operations, right, with that flavor of join, for example. And what happens at the same time Spark is generating its Java bytecode, right? You run your Spark, it generates Java bytecode to run in the CPU. Bigstream is taking that accelerator template and putting it onto the SmartSSD FPGA. And it's software configured. So that filter condition might be, okay, column 3, I want to be less than 0.5. Bigstream will, at the same time the Java bytecode is being generated by Spark, Bigstream will configure that template with that correct filter condition. So that's really how it works. It's a combination of precompiled templates and then software configuration at runtime. We call that runtime code generation, but that's really how it works.
Great. Thanks for that answer. Next question. How does the SmartSSD solution fare against GPU acceleration?
Interesting question. So, the way I think about it currently is that there's sort of, you can talk about in terms of speed up. I believe it's very comparable, but they're addressing sort of different problems, right? GPUs tend to be used for things like deep learning, machine learning, where there's very dense matrix operations, right? Where we've aimed the SmartSSD is at SQL and sort of more irregular, SQL-like operations, things with if statements, basically. And so they're looking at, and it's an interesting point, is that the hardware kind of dictates what it's good for in terms of its structure. I would say they're sort of very comparable, and there's starting to be some overlap where some of the ML is being executed on FPGA, and I believe that NVIDIA is trying to work with SQL on GPUs, but that's in the very early stages, and I haven't seen performance of that in this level of detail yet.
Yeah, I think Bigstream, you guys just on the 12th wrote an interesting blog post that breaks down the price performance comparison for a Samsung SmartSSD versus a couple different GPU solutions, and you're showing very favorable bandwidth per price performance, essentially 2 to 3x better bandwidth per price performance across. I think your comparison was against CSV parsing.
Yeah, Dan, can everyone still see the slides?
Yes.
Okay, so the link to that blog that Dan just mentioned is right on the slide there. And just as a preview, our next blog post coming, I believe, within a week, is going to talk about power performance, FPGA versus GPU. I guess you would call this almost SQL. It's for CSV parsing, comma separated value data parsing. And so we do a comparison of those two. As Dan mentioned, this blog indicates about a 3x performance price improvement with FPGA. You'll see even a wider margin in the power realm in our next blog post. So watch this space.
Fantastic. You inadvertently answered our next question. So great job.
Okay.
Stay tuned for the power.
What was the question
comparison? The question was, can you compare the energy cost impact of the SSD? It's a big deal for data centers.
Thank you. That's a point I probably should have brought up in my talk, and I appreciate the user. So there's data centers in whatever, London, Tokyo, New York City, that can't either be upgraded easily in terms of power. They can't move because they need ultra low latency network connections, and so acceleration is really an attractive alternative for getting performance, but the power has to be is a huge consideration. So, next week we'll be launching our blog on the power consideration. And really, these blogs are not meant to sort of attack any solution, right? We just want users, customers to think about these issues when they're thinking about acceleration. It's a relatively new concept, and so these are the kind of gotchas that you really want to think about when you're evaluating.
Awesome. Next question is a pretty detailed question. Does the FPGA SSD combo, so the Samsung SmartSSD, increase the SSD write speed by bypassing the hard drive driver?
Increase the what speed? And this is
the SSD write speed.
SSD write speed. I don't know the answer to that question.
Maybe you could answer it at an application level. What's happening?
Yeah, so at an application level, what you want to think about is there's like a little mini PCIe connection between the FPGA there and the SSD. And so you can configure, sort of automatically via, a bit somewhere in the PROM, right? You can configure the switch to either be in with the FPGA inline or bypass. So the speeds of the SSD are comparable, as my understanding, is comparable to a standard SSD of similar quality, of similar similar variety. But when the FPGA is put in line, I don't believe there's any effect on the read or write speed of the SSD. What's happening, as Dan mentioned, on the application level, is that you're getting processing of the data right on the storage. So I hope that answers your question. If not, feel free to contact us and ask more in detail.
Sounds good. The next question, which I can answer, is kind of a general SmartSSD question. Is it possible to accelerate arbitrary pipelines of OpenCV functions on a SmartSSD? And yes, you can do that, and you'll just need to leverage Xilinx Vitis development environment. The next question is
Dan, just to follow on to that point, it's a great point. So yes, Samsung is putting this platform forward as a generalized platform. I didn't want to indicate that Bigstream is the only way to go, but for the analytics piece, who might not be able to do sort of OpenCL or RTL programming, that's where Bigstream comes in. So yeah, glad we made that clear.
Cool. Yeah, so next question is a Samsung-specific question that you might be able to answer, Roop. How does the Samsung device enumerate to the system? i.e., does it show up as two separate devices, Samsung SmartSSD and Xilinx FPGA, or a single Samsung device?
I believe from the kernel's perspective, it shows up as a single device. The details of the connecting to the APIs, I wouldn't know that level of detail. But I believe, like, from the when you look at the devices on your system, it'll come up as one device.
Yeah, and for developers that are writing FPGA accelerated applications, they can use the Xilinx Vitis development environment to write an application targeting the FPGA on Samsung SmartSSD. But for end users that are leveraging that solution, it will show up as a single device, I believe.
Right, but you'll have access to sort of the FPGA shell, right, from that programming environment.
Yes. FPGA accelerated application developers will be able to target that FPGA, just like you can target the FPGA infrastructure as a service in Amazon with F1 instances, or in Azure with NPVMs, or an Alveo PCIe data center accelerator card. So next question is.
I think the single device, the single device approach is for transparency for sort of the DevOps users. We want to do like just an in-place replacement of their HDDs, right? So we want to just add another storage device, not sort of two devices. Yes,
certainly. So next question is, we've just got a large number of questions that just showed up. That's great. As the FPGA, let's see, is Vitis the only way to program the SmartSSD, or can you use Vivado? Vitis is the preferred method to program the SmartSSD. Next question: what real-world implementations with customers have you guys seen so far? Are there any kind of use cases that you see customers have been excited about?
Yeah, sure. So the couple, so first of all, for generalized analytics, certainly, this is an attractive device in terms of a simple upgrade, and so that's been, I can't name specific customers, obviously, but in terms of financial, and like I mentioned, data center, and with like there's an oil and gas that wants to upgrade their data center with this and offload that computation off of their servers, and you basically make a TCO appeal. And the other interesting one is some of the larger hyperscalers are evaluating the solution as something that could enhance their storage, their remote storage, right? So if you think about it, this could be some sort of a cache device where if not only are important pieces of data or reused pieces of data cached, but you'll have high performance computational access to that data by the computational element. So think about another tier of storage, and this is a large engineering redesign, but it's a very interesting one. So we have customers thinking about using this in that context as well.
Great. So we've got a few more questions that are very detailed Samsung SmartSSD questions that we'll follow up with directly, just because we don't have any presenters on that are from Samsung, and we don't want to misrepresent their product. So with that, I will thank our presenter, Roop. Thank you so much for the presentation, and thank you all all the attendees that spent time this morning reviewing the presentation as well as submitting your questions. If you don't feel like we answered your question sufficiently, feel free to reach out to us directly, and we will look forward to discussing Bigstream and Samsung Smart SSD solutions further. Thank you.
Thanks, everyone.